Welcome. Today, we're going to crack open the world of secret codes. If you're an educator and you've ever wondered how to explain something like online security to your students, or hey, even just get a better handle on it yourself, then you are in exactly the right place. We're going to be drawing from Dr. Sudheendra S G's excellent research material to really demystify cryptography and give you the tools to understand and teach these core concepts. Really, everything we're about to talk about boils down to this one simple, classic problem. How do you get a message from one person to another when you know for a fact that someone else might be listening in? That fundamental challenge, well, that's the very heart of cryptography. It's the art and science of secret writing. So here's our game plan for today. We're going to move through 5 key areas. We'll kick things off with why we even need secret codes in the first place. Then we'll get into the basic ingredients of crypto. From there, we'll look at some old ciphers and see exactly where they went wrong. And that will lead us right into the modern toolkit that powers pretty much everything, including that little padlock you see in your web browser.
All right, so first things first, let's talk about the why. Beyond just passing secret notes in class, why is cryptography so absolutely critical in our digital world today? What are we actually protecting?
Well, the reality is that no single security measure is ever perfect. It's just not possible. That's why the experts talk about a strategy called defense in depth. And the best way to think about this is to imagine a castle. You've got a moat, you've got high walls, you've got guards at the gate. But what if an attacker gets past all of that? Well, cryptography is the keep, that heavily fortified tower in the very center. It's the final, strongest wall that protects the most valuable thing of all, the data itself.
And here's the thing. This isn't some abstract theory. You are using incredibly powerful cryptography all the time, probably without even realizing it. It's that invisible shield that's securing your Wi-Fi at a coffee shop. It's the armored vault protecting your online banking. It's the digital lockbox that keeps your private messages meant for your eyes only.
Okay, so how does this stuff actually work under the hood? To really get it, we've got to learn the lingo first. The good news is there are really just 3 essential terms that form the foundation for everything else.
First up, we have plaintext. It's exactly what it sounds like. It's your original message just as you wrote it. Clear, simple, totally understandable to any human. This is your secret note before you've done anything to scramble it up. Now, once you apply a secret code, or a cipher, that plaintext becomes ciphertext. This is the scrambled, unreadable version. To anyone peeking over your shoulder, this should just look like a meaningless jumble of characters. Total gibberish.
So what's controlling the scramble? How do you turn that plain text into ciphertext and crucially back again? You do it with a key. The key is the secret ingredient. It's that special piece of information that locks the message up and is also the only thing that can unlock it. And this brings us to what is, without a doubt, the golden rule of modern cryptography. It's called Kirchhoff's principle. And what it says is you should always assume that your enemy knows your entire method, the whole system. Why? Because it is way easier to protect one small thing, the key, than it is to keep a huge, complex system a secret forever. The strength of your protection has to rely only on the secrecy of that key.
To really appreciate just how strong modern crypto is, I think it helps to look back. We need to understand why the old methods, the ones you see in movies, just don't cut it anymore. Historically speaking, ciphers pretty much fell into 2 main camps. On one hand, you had substitution ciphers, like the famous Caesar cipher, where you just swap every letter for a different one. So every A becomes a D, every B becomes an E, and so on. On the other hand, you had transposition ciphers, which didn't change the letters at all, they just shuffled the order they appeared in. But, and this is a huge but, there was a fatal flaw, especially with simple substitution. The fingerprints of the original language are still there. For example, in English, the letter E is the most common letter by far. So if you just swap E for, say, X, then all of a sudden X is the most common letter in your secret message. A codebreaker can spot that a mile away, and it makes cracking these ciphers shockingly easy. So how did we get past these flaws? Well, modern cryptography basically traded in those simple letter swapping games for some serious mathematical muscle. The crucial difference here is just scale. It's mind-boggling. Modern ciphers use keys that are so incredibly long that trying to guess them one by one, what we call a brute force attack, is just physically impossible. The time it would take to crack a modern AES key with today's computers is literally longer than the current age of the universe. But wait a second, this brings up a new puzzle. A kind of paradox, right? If you need a secret key to have a secret conversation,
But the only way you can talk to each other is over a channel that isn't secure. How do you share the secret key in the first place? Solving this was an absolute game changer in the history of cryptography.
So let's use a brilliant analogy for this. Imagine you and a friend are standing in a public square. You both decide out loud that you're going to start with a can of yellow paint. This is your public common color. Everyone can see it, everyone knows about it.
Okay, now for the secret part. You take the yellow paint, and without anyone seeing, you mix in your own secret color. Let's say it's blue. At the same time, your friend takes their can of yellow paint, and they secretly mix in their own secret color. Let's say it's red. Now you both have two different-looking new colors. And here is where the magic happens. You swap your new mixed paints right out in the open. Then you each take the can you just received and you add your original secret color to it one more time. And voila! You have both completely independently arrived at the exact same final color. It's a shared secret that nobody else can create. Because think about it, it's easy to mix paint, but it's practically impossible to unmix it. That whole paint mixing trick is a great example of what we call asymmetric cryptography. It's brilliant, but it's also kind of slow. So what modern crypto does is it uses a team approach. We use that clever, slow, asymmetric method just one time at the very beginning to safely agree on a new shared secret key. Then for the rest of the conversation, we switch to a lightning-fast, symmetric cipher, like AES, to do all the heavy lifting of encrypting the actual data. All right, let's put all the pieces together. Let's look at what is happening behind the scenes every single time you visit a secure website and see that little padlock icon pop up in your browser. It all happens in the blink of an eye, but it's basically a three-step dance. Step 1, your browser checks the website's digital certificate to verify its identity, to prove it's really who it says it is. Step 2, they use that public key magic we just talked about to create and agree on a brand new temporary secret key that will only be used for this one session. In step 3, they switch over to that super fast symmetric crypto to protect all the data that goes back and forth. So just remember, prove, agree, and protect.
So as educators, if there's one thing you want to impress upon your students, and honestly to remember for yourself, it's this set of rules. The absolute number one rule of crypto is do not try to invent your own. This is a field for absolute experts. You should always use standard, publicly tested tools, protect your keys like they are the most valuable thing you own, and always stick to modern, trusted algorithms. And that really leaves us with one final big question, doesn't it? We rely on these amazing mathematical systems to guard our most sensitive digital information. But what guards the systems themselves? Well, the answer is constant, unending vigilance. It's rigorous mathematics, and it's a global community of thousands of brilliant researchers who are dedicated to finding the flaws before the bad guys do. It's a never-ending race to stay one step ahead.